Good morning, everyone. So I'm here to talk to you guys about Ceph as part of the data infrastructure for zone storage. So let's start with the fun part. Let you guys glance at the fun part for a little bit and move on. So what I'm going to talk today to you guys about is motivated by the data-driven economy that, or world, as it were, that we live in today. So most of our activities day to day are driven by data-oriented new technologies, artificial intelligence, machine learning, etc. And this transformation is generating a lot of pressure in the data infrastructure. And I say data infrastructure because it's not just the storage of the data, but it's also the usability, it's the ability to consume that to generate revenue, which is why people pay for the storage. So that drives all those qualities that Sage was talking about before, that the Ceph project tries to achieve. Now, Western Digital, participates in all of these segments of the storage industry, and we're seeing this data growth and this pressure coming in all the different segments, from the high-capacity hard drives all the way to the fast-performance solid-state drives. And one of the things I want to note is we're seeing also this transformation in storage technologies from the types of interfaces being used and the paradigm that's used for the storage devices. In particular, we see this growth happening in SMR technology on the HDD side. Now, just out of curiosity, show of hands, who knows what SMR is? Okay, we're at the 30% mark. So SMR, that stands for shingle magnetic recording, is part of what we called zone block devices. So what are zone block devices? Well, in a normal storage device, it presents you a linear address space of blocks, typically 4K blocks. And you can do IOs. You write to them or you read from them. Typically, you can read and write in whatever order you choose. Now, there are performance implications and considerations that you'll try to do your IOs group together because locality usually improves performance. Well, zone block devices, they have this characteristic that they divide your linear address space of blocks into zones. Within each zone, you can only write sequentially. So you start writing at the beginning of the zone sequentially. If you want to, you cannot overwrite the data. If you want to write at those beginning addresses again, you have to erase the data, which is called resetting the data. So you reset the zone, and then you can start writing at it again. It's very simple. The reads can happen in any order you want. But the writes have this restriction that within a zone, you can only write sequentially. Now, needless to say, that kind of breaks backwards compatibility. So if you're going to take advantage of these kind of devices, you are going to have to update your software stack. OK, these are zone block devices. Now, why do you do it? I was perfectly happy with my I can write anywhere I want kind of devices. So the rationale is, well, it depends on what kind of storage media, but typically it has to do with efficiencies. Remember, growth of data, scale out, lots of use of data, cost of storage being one of the biggest infrastructure costs of a data-driven economy. So for hard disk drives, SMR, or shingle magnetic recording, allows us to continue the areal density growth that allows us to ship bigger and bigger hard drives. And the characteristics of shingle magnetic recording is that instead of writing each one of the tracks, the circular concentric tracks on a hard disk drive, independently, you overlap the tracks. By overlapping, you pack the data tightly together. Now, as a consequence, you cannot go back and overwrite one of the blocks in the middle. So what we do is we group these tracks into separate zones, and then zones can be rewritten independently, but within a zone, physically, you can only write sequentially. Now, when you come back to the solid-state drives, we have had this restriction of what are called erase blocks within SSDs since their inception. However, typically, within the device itself, you have what's called the flash transition layer that hides that fact from the outside world. Internally, it does remapping, it does garbage collection, it does wear leveling to make sure that all the different parts of the NAND arrays that you have gets used uniformly to increase the longevity of the device. Well, with zone device architecture, you no longer hide that inside the device, and rather you expose these erase blocks to be managed from the host system. Now, why would you do that? For a number of reasons. Part of it is you have systems on the host that are trying to manage basically where blocks are allocated within the storage device. And then internally in the device, you have another layer that's getting that first level of indirection and putting a second one inside it and reallocating data. So you have this log-on-log kind of a redundancy that generates very high what's called write application. You write somewhere, but then the device internally has to be moving it around as it does garbage collection and compaction. And the more you write, the more it wears out your device, and the shorter is the lifetime. So to gain efficiencies, you strive for a very low write amplification. And to do that, you want to expose this erase block structure up to the higher levels of the software stack so they can manage that and get the best efficiency on a global scale as opposed to a local scale inside the device. And when you do that, you reduce a lot of the pressures inside the device itself. Its need for DRAM, its need for having redundant blocks so that it can move data around. So all of these technologies are coming to the market so that you have more efficient storage. And these are standard technologies. Within the HDD industry, you have what's called zone block commands or zone ATA commands, depending if it's SCSI or SATA. And in the solid-state area, within NVMe, we have the zone namespaces that's being standardized. The standard isn't quite out yet. It's work in progress. We hope sometime maybe in the fall or something-ish, we will have this standardized. Cool. All right, so we've talked about these new technologies, not backwards compatible because it breaks the API. It's coming as the future of scale-out storage to increase efficiencies. And we've heard that Ceph is the future of storage. So it makes sense that we get Ceph ready to make use of these technologies. So to do that, we're looking at the shift to use BlueStar as a backend, and that being a better fit for us to integrate zone block technologies within Ceph. RocksDB has this LSM tree structure, which is natural for kind of zone block architectures. And then we're looking at incorporating some of the data structures for managing zone block devices within the BlueStar architecture. And we have a group of folks that started working on a project on this, together with a graduate student at CMU, Carnegie Mellon University, and some folks at Western Digital were starting to make contributions to the Ceph project in order to get it ready for the future of storage device technologies. And for those of you who want to learn more about what are these things and how is it coming, where, and maybe see some and touch some of these devices, you can talk to me. We have a booth at the floor, and you're welcome to join and contribute. Right, thank you.